Hello everyone, welcome to part 8 of my video series on probability distributions. So today I will talk about one of my favorite probability distributions, which is the exponential distribution. Now in order to understand this, you need to understand the probability distribution regarding the Poisson distribution, which I described in the previous video. So if you don't know about Poisson distribution, make sure to check that video. I will provide the link in the description. So let's dive in. So back to the example of Poisson distribution. Suppose my YouTube channel gets 10 new subscribers per day on average. That means lambda, or the rate parameter of Poisson distribution, will be 10 per day. We can get the probability of getting n, and n can be any integer. It can be 0, 1, 2, 3, etc. We can get the probability of getting n new subscribers per day using Poisson distribution, and it should be very straightforward to you now that you have gone through this distribution in my previous lecture. But what if we want to know the opposite aspect? So what is the opposite aspect? What is the probability of me getting one new subscriber within 2 days? So here we are trying to get the probability of getting one new successful event within some time frame. Previously in Poisson, it was how many subscribers per day. It has now been turned into how many days per subscriber in the exponential distribution. Another example for exponential distribution is the number of calls per hour in a call center. Suppose we get 5 calls per hour in a call center on average. What is the probability of getting one new call within the next 0.1 hours? And this is exponential distribution. So we are modeling time for each new event. So when we are modeling time, we know that time is a continuous variable. And so exponential distribution is a continuous distribution. So let's now derive the PDF, or the probability distribution function of exponential distribution, from the Poisson distribution. Let's assume that we get lambda calls per hour on average. So the probability of getting k calls per hour is simply going to be e to the power minus lambda, lambda to the power k by k factorial. This is per hour. Now if we talk about t hours, then the average number of calls is lambda t and not lambda. So the probability of getting k calls in t hours will be e to the power minus lambda t instead of lambda, and lambda t to the power k instead of lambda to the power k. If we get the first call only after t hours, suppose, just assume that we get the first call only after t hours, that means within t hours there was 0 call, k equal to 0. So if we put k equal to 0 in this equation, then we are simply going to get to the power minus lambda t. So just reverse it. Just think, if we want to get the first call within t hours and not after t hours, this is just going to be the complement of this probability, which is going to be 1 minus e to the power minus lambda t. But understand that this is equivalent to the CDF, or the cumulative distribution function of exponential distribution, because we are asking this question: probability of t less than equal to small t. That means, what is the probability of that event, of a single event happening within t hours? So when we are saying within t hours, this is naturally going to be the CDF. So CDF is 1 minus e to the power minus lambda t. Now how can we get the PDF of exponential from the CDF? Let's look at this notion. Now this particular curve has nothing to do with exponential distribution. It is just there to understand the concept. So if we want to get the CDF of x less than equal x prime from this PDF curve, then we are simply going to integrate, right? We are simply going to perform integration in this particular range, and we are going to find the area. That means in order to go from PDF to CDF, we need to perform integration. So in the reverse case, if we want to get from CDF to PDF, we need to take the derivative of the CDF with respect to the random variable. That is what we are doing here. We are taking the derivative of this CDF with respect to t, and that gives us lambda to the power minus lambda t. And this is basically, my friends, the PDF of the exponential distribution. So these are the PDF curves for different lambda. So as you can see, as the lambda increases, the curve sort of comes crashing down from the higher altitude. So let me just give you an intuition of why this happens. So a higher lambda means a higher rate of event. That means each new event occurs typically within a very short waiting time. So if lambda equal to very high, lambda is very high, that means the probability of an event taking a long time to occur will be very less probable. That is why this PDF curve actually comes crashing down. Now here is the expected value of the PDF. As you can see, it is nothing but 1 over lambda. So previously in Poisson it was lambda, and here it is 1 over lambda. This is very simple to understand. This is simply nothing but the average time per event, right? Because lambda was the rate of event per hour, and this is average time or average time in hour per event. Now I'm talking about hour because I'm just referring to the call center example, but you can use any other unit of time right here. The variance is also very simple. It is 1 by lambda square. Now let us do a simple math to understand the concept in more detail. Suppose this is an exponential distribution PDF and lambda equal to 10 subs per day. The question is, what is the probability of getting one new subscriber within 0.1 day? Within 0.1 day means this is CDF, that is probability of t less than equal to small t equal to this particular function. We already saw that before. And we can simply plug in lambda equal to 10 and t equal to 0.1 here, and we can get the area, this area basically. You can ask the reverse question, probability of getting one new subscriber after 0.1 day passes. This will just be the complement of 1 minus of the CDF, and this will be the right side area. But if someone asks us to get the probability of getting one new subscriber at exactly 0.1 day mark, then that will be 0. So we have also discussed this multiple times before when we talked about normal distribution, uniform distributions as well. For any continuous distribution, you cannot get the probability of the exact value of a random variable, because one new subscriber may have come at 0.100001 a day. We don't know that. It's impossible for him to come at exactly 0.1 day. Finally, let's talk about an interesting property of exponential distribution, which is called the memoryless property. Assume that I have been waiting for a new subscriber for the past 6 hours. The question is, will my probability of getting a new subscriber within the next 2 hours increase? Understand that I have already waited 6 hours. So if I wait 2 more hours, will the probability of getting a new subscriber increase? Now, common sense may tell us that yes, it should increase, but the truth is, according to exponential distribution, it will not increase. It is because the rate parameter lambda never changes with increasing waiting time. So even when I'm going to try and calculate the probability after waiting for 6 hours, the lambda never changes. And we can actually prove it mathematically as well. Probability of t greater than s plus t, that means probability of waiting another t time given that we have already waited s time. We can express it using the Bayes theorem. Now obviously you may think that this should be t greater than s plus t and t greater than s, but the intersection of t greater than s plus t and t greater than s is simply t greater than s plus t. Now we all saw this one before. This is simply nothing but e to the power minus lambda t. So a t can be replaced by these new times, and ultimately it is going to be e to the power minus lambda t. That means this particular value is the same as just waiting for time t. I mean, it doesn't take into account that we have already waited for time s. So that is all about the exponential distribution. If you like the video, make sure to subscribe and share. There's a donation link in the description as well. You can donate to our channel if you like our content. Thank you very much.